Hi, everybody. Great crowd. Very, very thankful to be here, part of your 20th anniversary of the Netherlands Java user group. My first time at JFall, so what a great show, and know a lot of you, and excited to meet a lot of you as well. Let's talk about developer productivity. My name's Justin Reock. For those of you who haven't met, I'm the field CTO, chief evangelist at Gradle. Spent a long part of my career writing code, doing enterprise architecture, that kind of stuff. And we're going to talk today about some theory around productivity. We're going to talk specifically about the myth of the 10x engineer. When I think about the 10x engineer, given the story that we're going to tell today, I really do put this engineer in the same category that I put the centaur, the Sasquatch, the chupacabra, the magical unicorn. I apologize if you actually believe in any of these things, but I do think that, societally speaking, they are generally accepted as myths. Where did this myth origin come from? Well, there is a kernel of truth to it like anything else, and we're going to talk about that a bit. There's a big write-up on the study that I'm about to dive into here at this QR code. If you are interested in it, you can look at a bit more of an academic look at some of this data. Okay. So during the 80s, a study was performed called the Coding War Games. Anybody heard of this study before? All right, a couple of you. Okay, so this study would look at close to 700 individual developers across about 100 different companies. And it was effectively designed to try to figure out some of the best and worst traits of developers. It was trying to figure out, who are the most productive developers within this workforce, and why are they so productive. The competition unit in this case was just a pair or a group of programmers working within the same company. Everyone was competing against one another, right? There were no paired programmers in this study. And effectively, everyone was allowed to choose, whatever means they wanted to perform in the study. They could choose whatever language, framework they were comfortable with, work within the normal conditions. A program specification was fixed, and participants were asked to log the amount of time that it took for them to complete the study. The results of this would feed into a book that I highly recommend. I think this is still one of the most important works talking about how to build highly productive software organizations. If that is of interest to you, I definitely recommend this book, and you can read more about the study in there. Okay, so what happened in the study? Well, the best programmers outperformed the worst by roughly a 10-to-1 ratio. All right, this is the kernel of truth to the 10x developer here. Before we look at some of the data, there were some really interesting non-factors in this study, things that you might think would impact the overall productivity of these developers that did not. First off, sorry, Java community, but the language actually didn't make much of a difference here. With the exception of assembly programmers, everybody performed at roughly the same level as long as they were comfortable with the framework. Years of experience, bitter pill for somebody like me to swallow, but the truth is that people working for about 2 years in the industry performed at roughly the same level as people working 10 years or more. Number of defects. Okay, are we just like completing this really, really quick, but cranking out a bunch of buggy code? No. The top performers in the study created defect-less code. And another bitter pill, salary. The top performers in the study were only earning about 10% more than the bottom performers in that study. Let that be a lesson. So what did matter? Well, paired programmers working within the same organization performed at roughly the same level. All right, this is where the myth actually bears out. The average difference within a single company was only about 20%. Which if you look at the range of performance from the top performers to the bottom performers, stretching actually we'll see 11x in this case. That 20% is statistically insignificant, right? So within the same organization, people were performing at roughly the same level. Now, they didn't work together on this task, but they came from the same organization, and the best organizations performed 11.1x better than the lower performing organizations. Okay. So what happened here? Harlan Mills, computer scientist from actually my state of Florida in the US, said, while this productivity differential amongst programmers is understandable, there is a 10-to-1 difference in productivity among software organizations. In other words, the best performers are clustering in some organizations while the worst are clustering in others. Some companies are doing a lot worse than others. And there's something about the environment, there's something about the corporate culture that's either failing to attract good people or, as we'll see, making it difficult for good people to perform their work effectively. That's probably, oh no, it's not too difficult to read. We're not going to spend too much time on this slide. It's in the book and it's in the study. I want to point out a couple of things. The answers that you're seeing on the left of this slide are the answers that were given by the people who were in the top performing, the top quartile part of this organization. On the right are the folks that were in the bottom performing part of this study. Look at simple things here. 76% of the top performing respondents said that they were able to divert their calls. Even in the 80s, this mattered. We had big chunky conference phones. Some of you remember them. You could divert them off and it meant you could keep doing your work, all right? 3 times as many people answered that they could do this in the top performing organizations. Do people often interrupt you needlessly? Only 38% in the top performing organizations said yes to this, whereas twice as many in the bottom performing organizations said yes to the same thing. Slack is not helping us be more productive. Okay, so what's the truth? What does the data actually bear out here? 10x organizations are manufactured, not born. Okay? If we pay attention to and we invest in the developer experience, we will end up with more productive software organizations. So let's talk about how we can do that and why this matters even more now than it did in the 1980s. Some of you might be familiar with this study. IDC is still pushing the 2024 study. I haven't seen a 2023 one come out. Basically said that by early last year, 65% of the global GDP would be digitally transformed. This bore out. It's closer to 70% now. It's one workforce is responsible for almost 70% of the global GDP, all right? This waste that we're talking about in the bottom quartile represents an astronomical number, all right? And most organizations aren't even aligned to properly discuss this. I was just having an excellent conversation with Margaret Ann Peggy Story from University of Victoria last night, talking about space framework, talking about the space dimensions, and the fact that we still don't have organizations that understand how to even classify the responses where people talk about productivity back into a framework like space, let alone take action on it. Who's familiar with space framework? Wow. Wow. This is probably the most modern and I would say the most accurate look at the way that we think about the productivity of a single organization right now. This is satisfaction, performance, activity, collaboration, and efficiency and flow. And the way that Space Framework works is that we gather data from an organization and we normalize the responses from that organization back into one of these 5 dimensions. In this study, which took place in April of 2022, a little bit more recent than the coding war games, we asked developers, how do you think about productivity in your job? We asked their bosses, how do you think about the productivity of your team? We took their responses and normalized them back into one of these 5 dimensions. That's how space works. It's very, very cool. You can gather the data however you want and normalize it back based on sort of a categorization exercise. What we found was disturbing. If you look at this, the answers between individual contributors and their bosses are quite different when we talk about the way that we think about productivity. All right, performance, the P in space, effectively means, are we meeting deadlines? Are we patching security vulnerabilities fast enough? Important stuff for the business, right? Predominantly, if you look at the right-hand column, this is what managers are thinking about. Versus individual contributors, developers. A lot of the people in this room are thinking mostly about activity, lines of code, builds, right? Stuff that we're doing. No one's thinking about satisfaction. Single-digit responses on both sides, okay? Huge, huge room for improvement here. And we know, for those of you who have studied productivity theory, if you've looked at things like the theory of constraints, if you've read books like The Goal or The Phoenix Project, then you know that the only initiatives that are going to positively impact performance of a business are ones that increase throughput while simultaneously decreasing the cost of that organization. DevOps and 12-factor and Agile and open source, they have not captured all of the bottlenecks to friction, productivity, and impediments to the developer experience that exist. Many of them are still hiding in plain sight right there in the developer experience. And a 10x organization needs to think about these things. They have to think about reducing build and test feedback cycle times and improving the overall consistency and reliability of builds. This is why it's time for developer productivity engineering. It follows in the footsteps of productivity theory to come before it. Practices like DevOps and Agile, change management, and business process management. All of these practices have in common the wisdom that if we can decrease the cost of an organization while increasing its capability for throughput, then we will always have a winning solution. All right. What makes developer productivity engineering different than a lot of the other productivity frameworks and approaches that are out there? I think the most important thing about it is that it starts with an understanding that software development is a deeply creative and satisfying process. Okay? It involves joy. It involves a state of creative flow. It involves norepinephrine and dopamine and serotonin, right? It involves pleasure chemicals in the brain. The brain has been mapped while developers are writing code. And it is this wonderful soup of left brain and right brain activity. On the one hand, we are doing something creative. We're holding a problem in our mind, and we're thinking about how we can solve it. And then we do something scientific, right? We create a hypothesis with our build toolchain. We say, I think that this code is going to solve this problem. And then we wait for feedback. We wait for that dialogue to be bidirectional. Now, in the case of these kids, maybe they did system.out.println hello world, or just println hello world if they're doing Kotlin. And it popped right out, and they said, yay, everything's great. Wow, look, joy, reward, experience. I'm liking what I'm doing. My feedback was instant. The experience is enjoyable. But put yourself in these kids' shoes, and I think you can. I think a lot of people in this room can empathize with that experience. The first time you ran a bit of program code and you asked for feedback and you got that feedback and it was positive, it was what you expected, it felt great, felt joyous. I want you to imagine that you're waiting 30 seconds, 45 seconds, a minute, an hour, 10 hours, the 72 hours that it takes for the Apache Tika project to run its full test corpus. You're going to look like this, and you're going to go look for a different hobby. Okay? And we need to improve this, right? This can no longer be the average calendar of the developer. And some people look at this developer calendar, this is fantastic. Where are all the meetings, Justin? But pretending that you actually get 2 hours a day to code, what does that really look like? All right, we're coding, we're in our flow state, we're happy, the dopamine's flowing, we're doing what we love to do, and then we're waiting. We're waiting for our build to complete. Then it fails. So then we get to spend the rest of the day debugging that failure, probably with inadequate tools and probably without enough data to understand what was going on in the environment that failed. Then we're going to go to lunch, play Elden Ring or New Zelda or Starfield, or I don't even know. It has been an amazing couple of months for games. We're going to go play, come back, we're coding, we're great, we're in our flow state again, we're where we want to be. We are waiting, but we fix our build. It completes this time, so we kick it to CI where we wait again for the CI build to complete. And tests are failing in CI even though they were succeeding locally. So now we get to do our favorite thing for the rest of the day, debug flaky tests. What a wonderful life. We have to get out of this, all right? I love this cartoon. This cartoon's everywhere. Everyone's using this cartoon to talk about productivity because it's really relatable. You know what else it is? Really, really sad, okay? Because it's true. And maybe if this isn't your life, maybe your life's more like this instead, right? I have a sinking feeling that we might be heading here. I hope not. It's up to us. All right, before we start actually digging into the meat of this theory, let's make sure we're really, really clear on what we're solving. All right, if you can imagine that this is a developer on the left, and we're sort of painting a picture of their experience. The thing floating around that developer are the basic quantum unit of developer experience, the feedback cycle, that dialogue that we talked about before. All right? Sometimes things are fine. Do I have a lasery thing? Yeah, I do. Sometimes things are fine. Sometimes they take too long. Talked about that. Sometimes they take too long to fix, okay? Just because the build goes red doesn't mean that we're immediately out of our flow state. Just another problem to solve. That's why we're here. We love to do that. But if 45 minutes later you're still waiting on a Slack from some build engineer or CI engineer, or still scanning the environment for some piece of data that you need to solve the problem, that is not flow state. That is friction, frustration, and toil, and we need to eliminate that. Then the worst one. The worst one right here, the problem, the wasted energy and time that could have been prevented with a little bit of analytics, a little bit of proactivity, the flaky test, the avoidable failure. All right? We're going to deal with all of these. And why are we going to deal with these? Because feedback cycles are really important. Speed is really important in the feedback cycle, but why? Right? We don't always talk about all of the new behaviors and effects that we should expect when we do something like improving feedback cycle times. All right? We got some obvious stuff here. Less idle and wait time for our developers, sure. What does that really mean? It means less context switching. Familiar with that term, context switching? Taking your mind from doing one thing to doing something else, right? We don't do that instantly. We're really bad at it. It takes about 10, 15 minutes for our executive functioning to truly switch focus onto another task. It's a tax of context switching. Guess what happens if we have a long build cycle time? We pay that tax twice. To wait for our build to complete, now our brains go off and do something else and switch. Now the build's complete, we go back to our work. Anywhere from 20 to 30 minutes lost just because of that one cycle time. So not only are we really bad at this, but we found out over the last couple of years that it's really bad for us to try to force our executive functioning to do this. Context switching is associated with an increased amount of glutamate in the prefrontal cortex of the brain, which is directly associated with cognitive fatigue. And the thing about cognitive fatigue is that it's difficult to detect. All right? When people are fatigued, they can still perform basic tasks. They can still do the jobs that you give them, but it's really hard for them to innovate. It's really hard to elevate the work that's being done. So there's a direct relationship between the cognitive fatigue of the engineers working on a project and the capability for that project's innovation, which means there's a direct relationship between feedback cycle times and the overall innovative capability of our planet. Okay, so we need more focused developers. What about this? What about the less obvious stuff? Well, the thing is that if builds are happening faster, developers tend to build more frequently. Because what is the build? It's the dialogue with the tool chain. It's the opportunity to refine the work that we're doing. It's the opportunity to figure out, is what I'm doing of high quality, right? So being able to do this more often is a good thing, because we end up with smaller change sets, right? Which means fewer merge conflicts and more efficient troubleshooting and a faster mean time to resolve of issues. All of this leading to better productivity, better quality. All right, we're going to talk a bit about the technology that can do this. I have a whole session on this that will dive in deeper with demos and everything. I think it's like a 5 o'clock-ish session. It's the speeding up Maven, Gradle, and Jenkins with a build cache session. So we'll dive into this more. The main takeaway I want you from this keynote is that a build cache is not a dependency cache. I love my friends at JFrog and Sonatype. Those are great products. They're not the same thing. Okay? A build cache is actually caching chunks of the finished artifact. Who's turned this on before? It's free in the open source Gradle build tool, org.gradle.caching equals true. Maven just released one, generally available as of October, I think last year, right? Dive into this thing. It's going to allow you to pull parts of your build artifact from cache as opposed to rerunning parts of those build. All goals and tasks are directed by a set of inputs. Source code, JDK, class path, compiler arguments, whatever it is. I want to create a hash from those inputs, and I want to take the output that was created from that part of the build, stick it in a cache somewhere so I can pull it later. We're talking anywhere from 40 to 90% reduction in build and test cycle time just from turning on caching alone. All right? There's all kinds of stuff that can become an input to this caching, including tests. Right? In this case, we're just looking at Maven goal inputs and Gradle task inputs. But there's a lot of potential here for savings. I'm going to whip through this just in the interest of time. We're going to look at kind of a quick example of how caching can help you, and we're going to dive into this in the 5 o'clock-ish session. I should probably know that. What you're looking at here is how most programs behave without caching. Imagine that this is a 4-module application. These arrows direct the dependency relationship. We have a core module. Export API relies on the core module. Service depends on core. Web app depends on service. Nothing depends on web app. Under normal circumstances, a Maven build or a Gradle clean build, notwithstanding Gradle's up-to-date or incremental capabilities, this is what happens when any change happens anywhere. Every single one of these tasks or goals has to be rerun. Well, when we're caching things, what if we made a change to the public method in the export API module? Well, we have to recompile that code and recompile its test, run its test and check style the source, but we don't have to do anything else. All of this could get pulled from cache, right? Similar, public method in the service module, upon which web app relies. Well, We do have to recompile, service and recompile web app, run some test compiles and run our tests, but all this could be pulled from cache, all right? Implementation detail of the service module, even less invasive change. And this can be done remotely too, right? We live in a world of ephemeral environments where we're building our code in things that last for like 5 seconds and then go away forever. Makes it really hard to troubleshoot. When we have something that's remote, we can instead share that node across ephemeral agents. What else can we do? We can distribute our tests. Anybody seen the test distribution pattern yet? It's very cool. Kubernetes makes this super easy. Effectively, what we can do is go beyond single machine parallelism, or things like multiple worker threads, and things like CI fanout, right? And instead, we can build local, right? And within the local environment, we can be distributing tests out cloud scale. We can talk about this too. Netflix put this in place a year-ish or so ago. They took a 62-minute test cycle time down to less than 5 minutes, just with a combination of a test distribution pattern and open source build caching, okay? Pretty good. And of course, machine learning is going to make things even more efficient. We'll get the slides available for you. Sorry, but it's in the interest of time. Predictive test selection. Anyone heard of this approach? Really good white paper available from Facebook, one of the companies that pioneered this technology. They'll show you how to build the model from scratch. Effectively, this is going to allow you to predict whether a test is going, with reasonable accuracy, whether a test is going to succeed or pass based on your changes before you actually run it. The upshot being, if I have 10,000 tests, but only 20 of them are going to fail, why am I running all the rest of those tests if they're just going to succeed? All right? If I can predict with some reasonable accuracy that they're not going to provide anything valuable. Conventional test selection would, out of an abundance of caution, run all unit tests associated with module changes, whereas predictive test selection is going to generate effectively a likelihood of a unit test failing when certain changes occur and only run those tests. So we're going to optimize our test set. And finally, build scans are going to speed up our ability to do troubleshooting. This is my Gradle plug. I think many of you may be familiar with build scans. If not, check them out. They are free. Okay, we have to keep an eye on this stuff too, because it's not like a one-time fix of our build is going to keep things fast forever. Any number of things could be introduced to the build that could slow things down. For instance, we might upgrade our annotation processor and suddenly builds take twice as long as they did before. Do you know what happens usually now when something like that occurs? Absolutely nothing. Usually when a build goes from 5 minutes to 10 minutes, nothing happens at all. It's either not observed or it goes reported, but no one does anything about it. Or even if it gets reported, no one can figure out when it got so bad. But you can observe quite a bit just by watching. The truth is that none of us are. Who's tracking local build times? Who's actually tracking that metric? How long developers are waiting at their laptops for builds to complete? I got to tell you, the 10 or 15 people that raise their hand is like 12 people more than I usually get. No one's doing this. All right, this is a blind spot. So you should be excited because we have a new thing we can watch and improve now. You should be doing this. 10x organizations do it, and they put it on a table so that it's easy to visualize. Because we know that you're not going to like what you see if you start doing this. This gets us out of the wrong mentality. Is the cycle is fast enough, which is what we ask now. Gets us into the right mentality. Is the cycle as fast as it can possibly be given all data, acceleration technologies, observability, analytics, and optimization? All right, 80% of the people-ish that we surveyed who are already doing DPE said it made their job more enjoyable. I don't think that should be surprising to anybody if you think about what we're talking about here. The last bit that I'll leave you with is the analytics component of all of this, which is the forward-thinking ability to take a look and record things like, for instance, failure behavior or flaky tests, because this is what we do now. Is it not? And I think that you'll see that there are means by which we can detect these, put them on boards, and follow processes that will allow us to proactively eliminate sources of frustration, such as flaky tests. And DPE will become standard practice. The world should foster developer joy. And there's some next steps that all of you can take. The biggest one is to think about this in terms of a central organization with leadership mandate. If you need help with any of that, I'm around. I've talked to lots of pointy-haired bosses about how quickly they'll make their money back by putting a policy like this in place. We do have a cool program where you can learn more about DPE step by step and get rewarded to do so. Cool Legos and Gradle swag and stuff if that's your speed. And of course, there's the DPE handbook, which you'll see Gradle's logo on the front of it. The rest of it is not branded, vendor agnostic, and all those things. Thanks very much. I really appreciate the time today.